Okay, so this is the third session on the behavior of gases and the last one for the C work, where we finally start to combine what we've learned about pressure and temperature and volume in the last three sections. So we're going to learn how to use, well, what the gas laws are and then how to use them. Now, there are three gas laws that all relate to one another. You have Boyle's law, which is the first pressure times the first volume is equal to the second pressure, P2, times the second volume, V2. So usually the way we say this is P1 V1 equals P2 V2. And it's assumed you multiply between the two of them. Charles' law is a relationship between volume and temperature. So the first volume divided by the first temperature will equal the second volume divided by the second temperature. And then the last gas law is Gay-Lussac's law, which relates pressure and temperature. And pressure and temperature have this relationship. Oops, 2. And this should be divided by also. Okay, so these are the three gas laws. Now, there's an easier way to go about them. I don't really care about the names, and there's no need to memorize these three gas laws because ultimately you can put them into one called the combined gas law. So the first pressure times the first volume divided by the first temperature equals the second pressure times the second volume divided by the second temperature. Now this pressure can be in anything. The pressure can be in atmospheres, it could be in torrs, it could be in millimeters of mercury, it could be in kPAs. Alright, so those were all the main units we practiced. The volume in these, the volume can be in milliliters or liters. And the temperature in these problems always has to be in Kelvin. Okay, we can't have any temperatures in Celsius because then you would get negative pressure and negative volume, and you can't have negative numbers for pressure or volume. And if you refer back to the periodic table, again on the back side, we're ripping through these formulas, you can see you have the combined gas law there. So if you have the combined gas law, you can do any of the three other laws, Boyle's, Charles, or Gay-Lussac, or combine the three of them. So let's take a look at a problem. What is the volume of a gas had 2 atmospheres and 200 Kelvin if the original volume was 300 liters at 0.25 atm and 400.0 Kelvin? Now, when you have one of these problems, it's best to make a list. Okay, make a list of all your variables. We've got P1, we have V1, we have T1, and then we have P2, V2, and T2. Okay, so those are all the variables, and we start picking things out that we know. So we hit the first thing. This is 2 atmospheres. Well, atmospheres is a pressure, so we can say 2.00 atm. And our next thing paired up together with the 2 atmospheres is 200 Kelvin. 2.00 Kelvin. Okay, so those are the first pressure and the first temperature. And it's asking what's the volume of the gas when we're looking at those two numbers. So if we read the rest of the problem, it says the original volume was 300 liters. So there's 300 liters at 0.250 atm and 400.0 Kelvin. Okay, so that's our problem there. So we are looking for V1. So the best thing to do is to get V1 by itself. And let's do some reciprocals here so we can get the T and the P to cancel out. What you do to one side, you have to do to the other. So T1 and P1. So those cancel, T1 cancels, and I'm left with V1 equals P2 V2 T1 over T2 and P1. Okay, so there's our problem there. Alright, now it's real easy just to go back in and substitute numbers. V1 is equal to P2, so look at the list, 0.250 ATM. V2, well, V2 was 300.0 liters, and T1 was 200 Kelvin, like that. And then on the bottom, T2, 400.0 Kelvin, and T2, oh, that was T2, P1, which is 2.00 atmospheres. So remember, you multiply for every number on the top, and you're going to hit divide both for the 400 and the 2.00 written on the bottom. And you multiply the numbers on the top divided by the bottom, and on the calculator you get 18.75. Okay, so now we need to go back and look at our significant figures. The least amount of significant figures that I have are the 2 atmospheres and the 0.250 atmospheres, so I've got 3 sig figs I should have in my answer, so that becomes 18.8, and my units, atmospheres cancel out, kelvins cancel out, and liters is what I'm left with. Okay, so these are very easy, simple problems to solve if you're orderly. Okay, that's the key. Students want to save time and they skip this list and then they start to mix up numbers. Okay, if you don't want to make the list, then what you need to do is you need to practice then labeling in the problem like this. T1, or let's see, that's P1 and this is T1, and then you call this T2, V2, and P2. You need some way to label them, that way when you start to plug in the number, keep everything straight. Okay, let's do one here. A container holds a volume of 2.5 liters at 250 Kelvin. What size would the container have to be to increase the temperature to 300 Kelvin while keeping the pressure constant? Now, this is really important here. You're keeping the pressure constant. That means pressure is going to not be part of this problem. And you're left with V1 over T1 equals V2 divided by T2. Okay? And when you do that, you see, since pressure is constant, you're left with Charles' law then. So, we've got a volume of 2.5 liters. Well, let's V1, and it's at 250 Kelvin, so we'll call that T1. What size would the container have to be? Well, the size is the volume, so that's V2, to increase the temperature to 300 Kelvin. That's T2. Okay, so we've got this equation here, and what we're looking for is V2. Now, it's always best to just move your numbers or your letters around before you start putting numbers in. So, I know what some people like to do is they like to cross multiply and bring everything up to the numerator, like so. Okay, again, always look back. We're looking for V2, so we want to get V2 by itself. So that means T1 cancels, and I get V2 is equal to V1 times T2 divided by T1. Okay, so I go ahead and plug that in. V2 is equal to first volume. Here's first volume. 2 pointers times the second temperature, T2, 300 Kelvin, divided by T1. There's T1, 250 Kelvin. So multiply the numbers on the top, divide by the numbers on the bottom. V2 is equal to 0.0 liters. Okay, because you cancels out. And you have 2 sig figs with the 2 liters. That's 2 sig figs. And I should have 2 sigs in my answer. So 0.0. Okay. Alright. So, alright, what cons doesn't even fit. The other, okay, ideal up here. Okay, so PV equals nRT. So pressure, volume, we've done those before. N is the number of moles. T is temperature, okay? And then R depends on what you're using in the problem. R can be 8.31 or 0.081. It depends on what you're using for units. So there's kilopascals or atmospheres. So pressure, so we'll put it here. Pressure has to be, in this case, in atmospheres or kPa. If it's in atmospheres, you're going to use 0.0821. If it's in kPa, you use 8.31. Volume has to be in liters, always. N is measured in moles. R is those constants there. It's known as the ideal gas constant. And T has to be in Kelvin for these problems. Okay, so you'll see on the back of your periodic table, you've got the ideal gas law. It does not have R written down, the R constant, so R would have to be given to you as part of the problem. Okay? So here's an ideal gas law problem. In fact, let's write it up there. PV equals nRT. You fill a rigid steel container that has a volume of 20 liters with nitrogen gas to a final pressure of 2.00 times 10 to the 4th kPa at 28 degrees Celsius. How many moles of N2 does the cylinder contain? So, same thing. Make a list of units. Oops, I forgot the N. There's the R and the T. So pick out what we know from the problem. Volume of 20 liters. That's easy. 20 liters. Pressure right there. 2.00 times 10 to the 4th kPa. Okay, and then since this is kPa, kilopascals, R has to be 8.31. And then we're looking for moles. It says how many moles, so that's where the question mark goes. And my temperature is 28 degrees Celsius, so I have to do 28 plus 273 equals 301 Kelvin. Okay, so we're looking for N here. So we want to get N by itself. So let's divide our formula by RT. So the R cancels out, the T cancels out, and I'm left with N equals pressure times volume divided by RT. So let's go ahead and solve that. N equals pressure, 2.00 times 10 to the 4th. Volume, 20.0 liters. My R is 8.31. And then my temperature is 301 Kelvin. So we multiply the numbers on the top, divide by the numbers on the bottom, and you get 159.916. And if we look at the problem here, we've got 3 sig figs in the problem, so this becomes N equals 160 with a point moles. Okay, so that's how you solve an ideal gas law problem. Let's do another one. So a container holds 1.280 moles of methane gas, and it holds 2.24 times 10 to the third liters at a temperature of 42 degrees Celsius. What's the pressure inside the container? So again, make a list of your units. Okay, since it's an ideal gas law container, and pick out what we know. We know the number of moles. Right there, 1,280 moles. We've got our liters. Our liters is volume, 2.24 times 10 to the third liters. Temperature, 42 degrees Celsius. So we have to change 42 degrees Celsius into Kelvin. So we add 273 to it and we get 315 Kelvin. And it says, what's the pressure inside the container? Well, it doesn't say what it wants the pressure in, so we can just assume atmosphere. Assume atmospheres, then R is going to be 0.0821 for our gas law constant. So this time we want to get pressure by itself, so we need to divide both sides by V, and we get pressure equals N times R times T divided by volume. So let's do our N. 1,280 atmospheres, our R, 0.0821, our T, 315, divided by our volume, 2.24 times 10 to the third liters. And you multiply the numbers on the top, divided by the numbers on the bottom, punch it out in your calculator, and this is the start of the number that you get, 14.778. And if we look back at our problem for our significant figures, that's 3 sig figs. So should equal 14.8 atmospheres for the units. Okay? So one last thing here, now you've got two formulas, so how do you know when to use? Okay, when you've got two formulas, what you want to do is read the problem closely. When it talks about two pressure, two volumes, or two temperatures, you're going to be using the gas law. Okay, and in addition, you change that. Talking about moles, problems talk about grams, that pointing the gas law, especially if it starts to talk about R. If it gives you an R value, then you know you're going to be doing PV equals nRT. But with the combined gas law, pressure over volume, or pressure times volume over temperature, pressure times volume over temperature. Okay, and if it says it's constant, you cross it out. Or if it doesn't bring up temperature, then you cross out temperature and you just work the problem with pressure and volume. The combined gas law is really nice because it's flexible that way, and you just cross out whatever you don't need and solve from there. So at this point, I want you to go back to your graphic organizer and make sure you complete the section on the gas laws. You need to include both the combined gas law and the ideal gas law, putting the R values in.